Wait, okay, 1 second. Sorry, I'm opening TikTok to make sure you didn't answer me back. Okay, you didn't. Okay, cool. So, we, oh, we are gonna work on diagonalizing this very straightforward matrix, okay? And the rules work the same for any size matrix, but it's just easier with the 2 by 2, so we're gonna start with that because he's really not gonna be um, probably giving us much more difficult than that. Maybe 3 by 3. So our first step of trying to diagonalize, you can't see what I'm doing, can you? Okay, diagonalize a matrix is we want to find the eigen values, not vectors, sorry. So we're going to find the eigenvalues. So the way we find the eigenvalues of this matrix is this lovely equation that really doesn't mean that much to me, but it is the determinant of A minus lambda I, okay? That's a really fancy way of saying you get the determinant of A, which is what this matrix is. So you put 6, I'm going to give some space, 6, 0. Oh, sorry, you can't see it too well on the screen. 6, 0, 10, and negative 6. And then that lambda I just means that you are subtracting lambda times the identity matrix. So it's 6 minus lambda, negative 6 minus lambda. It's only on the diagonals because the identity matrix, if I was to have a lambda I, it would look like lambda 0, 0, lambda, right? So that means that when we try to calculate the determinant, we're going to be calculating the determinant of this thing. Okay, so if you remember how to calculate the determinant of a 2 by 2 matrix, you can use cofactor expansion for anything bigger than that. But for this, you just multiply. You cross multiply, so 6 minus lambda times negative 6 minus lambda. And then you subtract the other diagonal. So it's minus 10 times 0, okay? And believe it or not, this gives us 0 right here. So we're left with 6 minus lambda times negative 6 minus lambda. Okay, now this doesn't really help except for the fact that when you're finding the eigenvectors, you're looking, or the eigenvalues, sorry, you're looking for where the determinant of A equals lambda I equals 0 specifically, okay? So we're going to set this equation equal to 0. And if you've done algebra, you would probably recognize that you can find the value of lambda by basically setting each part equal to 0. So 6 minus lambda equals 0 and negative 6 minus lambda equals 0. Since they multiply together, you are allowed to do that mathematically. And basically, you add lambda to both sides, plus lambda, and then this side you plus lambda, and you're left with 6 equals lambda, and negative 6 equals lambda. Okay. These two things are our eigenvalues. Congratulations, you figured out your eigenvalues. Okay, now we're going to move up over here to this side of the thing. I'm going to write down our eigenvalues again, which is negative 6 and 6. And now we want to find where in our original statement do they correspond to. So you see how it was like, okay, so this was our original A. It was 6, 10, 0, and negative 6. Okay. So we're trying to get it so it takes the form of something along the lines of something. So I'll put like an X, 0, 0, Y. Okay, we just want the diagonal to have variables. Everything else needs to be 0. So the way we get that is by, well, we're getting our eigenvectors is what we need. Basically, your eigenvectors make up your diagonalization. So you have some, okay, when you're diagonalizing an equation or a matrix, you have A, your original matrix that you're given, times some P, which doesn't mean a whole lot until I explain it a little further, times D times P inverse, okay? So if you're trying to diagonalize a matrix, D is this diagonalized matrix. This is our goal, okay? And currently, we know that this matrix is going to have our eigenvalues in it. So we actually know what D is going to look like. It's going to be negative 6, 0, 0, 6, or it can also be 6, 0, 0, negative 6, okay? Doesn't matter what order they're in, as long as you stay consistent with this, okay? It doesn't matter which one you choose, but you have to keep it in mind when you're working with it. Our goal is to find the P. This is what matters. Don't worry about P inverse. We can find the inverse using our calculator really quickly, but we need to find our P. P is made up of the eigenvectors, okay? That's very important. The way you find your eigenvectors is you plug in lambda. So you remember how it was A minus lambda I? Well, that's how we found it originally. Well, we can, oh, what did I do? Sorry. Okay, we're good now. Well, we can use this to our advantage here. Okay, so we're going to take our original thing. Okay, so we're going to have 6, 10, 0, and negative 6. But this time on the diagonal, because of this, we're going to subtract each lambda. So for this one, we're going to say 6 minus 6 and negative 6 minus 6. And then we're going to have a separate, let me scroll down, a separate matrix that has the other eigenvector, or value, sorry, eigenvalue. So this is going to be 6 minus negative 6, 0, 10, and negative 6 minus negative 6, which, let's simplify. Let's work with the top one first. Okay. Sorry, I accidentally wrote that. So that's going to simplify to 0, 0, 10, and negative 12. Okay. And then we'll simplify this bottom one. Okay. 6 minus negative 6 is 12, 0, 10, and negative 6 plus 6 is going to be 0. Okay. Notice how they look pretty similar? That tends to happen. Our next step in the process is to take the RREF of these things. So we want to take the RREF. I'm sure you remember how to do that. You go into your calculator, you plug in matrix 2 by 2. We're going to have 0, 0, 10, and negative 12. And then RREF. Oh, sorry, I'm taking my time. I did not have this prepared, unfortunately, because I am not a math professor. Not yet, at least. But it's going to give me 1, negative 6/5, 0, and 0, okay? I'll worry about the other one later, but right now we'll focus mainly on this first one. So we can make this augmented and say that is 1, negative 6/5, 0, 0, and then have a 0 and a 0 over here, okay? If we want to solve for our free variables, which in this case, this is our free variable because there's no pivot in this column, I'll say that x1, okay, is equal to x2 times negative 6/5. Okay, you see where that comes from? But the thing is, this is actually a positive 6/5 because you're moving it over to where the augmented matrix is. So there's actually a secret step in here where you go 1, 0, you 0, 0, 6/5, and 0. Okay? Now, this is a weird thing. You might have noticed this earlier in the class. But if you're taking something out of x2, this is where x1 was, right? Well, x2 is going to go here. So you'd put a 1 here because there's always going to be 1 associated with x2, okay? So if you were working with x1, you would put the 1 at the top and the 0 at the bottom, or whatever it is. I can explain that more in detail later. But basically, it leaves you with this. And I don't know if he is okay with you leaving it like this, but I know that Pearson, like my lab math, is not. So what you want to do is you just want to get rid of the fraction, and you want to leave it x2, and you want to multiply both the top and the bottom by 5, which will give you 6, and then 1 times 5 is 5. So this is your first eigenvector, okay? Now, all we have to do is do that again over here. So we're going to go back and take the RREF of this matrix, which is 12, 0, 10, and 0, right? Take the RREF, and this one is a little more interesting, actually, because you're left with 1, 0, 0, and 0, okay? Now that can be weird, right? You have a lot of zeros in there. You don't know what to do with. If you augment it, it's going to go 1, 0, 0, 0, 0, 0, right? You have a lot of zeros. Well, if we were to turn this into a form of x2, because there is a free variable here, right? Well, you're going to have 0 for the first term, right? Because 1 equals 0x2. That's what this is saying. But like I said earlier, you always have 1 for the spot of that variable. So if it's x2, x2 is equal to x2. So you put a 1 there. If it was like, if you had 3 and x3 was your variable, and your first two were the whole thing was zeros, you would still put a 1 in the last spot. Okay? So now these are our two eigenvectors, okay? Now we use these to form a matrix. It's not as bad as it sounds, but this is where you need to keep in mind what your diagonal matrix looks like, okay? So let's say we chose to have it look like 6, 0, 0, and -6, okay? Let's say that's what our diagonal matrix looks like. Well, when you plugged in 6, you got this eigenvector, right? So when you're creating your P, you want it to be 6, 5. And then when you plugged in -6, it gave you that one. So you put, oh, I accidentally turned off my iPad. You put in a 0 and a 1 here. And I have our answer actually down in the corner over here. But you'll see 6051 is our answer. That is what my lab math told me it is, and it is correct. So we did it. If you have any questions, just let me know. So yeah, awesome.